Good morning. Looks like maybe a midterm is coming up. So yeah, we got a midterm coming up in the very near future. We've got a set of practice problems, problems from a previous year's midterm. And so, and there's a key, this is all in Canvas, so you guys can track all these things down. But here are these practice problems, and let's take a look. There's solutions that go along with this. So this is midterm 3 that's coming up, and the first problem we run into here is looking at one of these circuits. So we've seen examples like this before. This is looking kind of like a chapter 26 problem maybe. And then down here it looks like maybe we've got an RC circuit. So again, a couple of problems, mostly from chapter 26 more so than 25. But you should be prepared for either types of problems. But let's go ahead and take a look at the problem here. So if you go back and look at that circuit that was given, there's 3 branches. Now we've looked at an example with 3 branches before, maybe a couple times, V1, V2, and V3. And each one of these has a resistor in it. So I kind of rewrote this in a way where it looks simple. I'm hoping that makes it look simple writing it that way. And then as always, you know, I always like to draw these current directions in, and that's actually something you need to do. I decided to go with this. What I noticed was, you know, a lot of times I'll try and get the current to go forward through a battery. That's always a good thing to look at, is that the batteries are going to be driving currents in this direction, but they can't all drive current in that direction because all the current would end up on one side of the circuit. So there's got to be current going backwards through one of the batteries. And so I went with battery 3. Battery 3 was only 2 volts. And so I thought, why not? Let's define, oh, I did it with 1 and 2. Okay, now I'm getting more. Oh no, I'm sorry. Voltage 3, 2 volts, is down here. So yes, what I've got is these 2 batteries, I'm going to say, are successfully driving current I1 in this direction, I2 in this direction, but they're going to overwhelm the battery here, and the current's going to be driven backwards through that battery. I hope it's a rechargeable battery. We'll get that energy back again. So what we've got going on then is I1 and I2 join together right here and become I3, which travels here, and then it separates again into I1 and I2. So that says that my current equation is going to be I3 is equal to I1 plus I2. Now, I need to come up with some loops, and the loops I chose were these. Here is loop number 1, here is loop number 2. For loop number 1, I like being able to set up the loops in a way where the loop is following the direction of the currents. So with current 3 coming back in this other direction, I decided to pick loops that would go all the way around, the first one. So that would be following I1 here and following I3 here. And that means when I set up these equations, I don't have to think about minus signs. As long as I'm going in the direction of the current, I don't have to worry about minus signs showing up. Now, I also picked a loop, loop number 2, is going this direction through the lower portion. And again, my intention here was to make the problem easy, minimize the number of minus signs. Now, the way I set up the loop equations, and you guys have seen this because we've done a couple of these examples, is to say the voltage boosts in each loop are equal to all of the voltage drops. So every time we go through a battery, we get a voltage boost. And then every time we go through a resistor in the direction of current, the voltage comes down. So what happens with any loop is if I look at the boosts, they've got to match the drops. I mean, it could be in stages. It could be the battery goes through and it drops through some resistors, but then there's another battery and it comes back down. But by the time I've closed the loop, everything cancels out. And so for loop number 1, I guess I'm calling it, loop number 1, we've got a V1 minus V3. Now V1 minus V3 gives us a 6. For loop 2, it's going to be V2 minus V3, and that's 12 volts minus 2. So my two voltages, the voltage boosts, in loop 1 is going to be 6, and loop 2 it's going to be 10. Now what are all the voltage drops? And so, so instead of writing, 6 minus 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 equals 0, I like doing the voltage boosts on one side and the voltage drops on the other, and then just setting them equal. Either way, of course, will work, but I do favor this approach for myself. So what we can see with loop 1 is that loop 1 has this resistor. It has R1, and R1 is 4 ohms, and that's acting on current 1. Loop 1 also has R3, and R3 is acting on current 3. So R1 current 1, R3 current 3. Now, we did the same thing with the lower loop. We put in the R2, I2, and the R3, I3. Those are here. And now what we can do is we can use our current equation. The current equation says, hey, I can eliminate one of my unknowns. I can eliminate I3, and the way I can eliminate I3 is by replacing it with I1 and I2. So in this equation, I replaced the I3 with I1 and I2. And then here also, I replaced it with I1. I switched directions here. And then what those became, I rewrote the equations right here. So now it is 6 is equal to 5 I1s plus an I2. And 10 is equal to an I1 plus 9 I2s. And I'm using that trick where you take the two equations. I want to eliminate I2 from these two equations. So what I'll do is I will look at the coefficients and then flip them and then multiply the entire equation by those numbers and then take the difference between the two equations that are remaining. So that would mean 9 times 6 minus 1 times 10. And that left me with 44. Now, what happens with the I2s, if I take 9 times 1 and subtract 1 times 9, that goes away. And that was the plan. So the I2s are gone, and 9 times 5 minus 1 times 1, that's going to leave me 44. Oh, look, it's going to be one of those easy problems with currents that are easy numbers to write down. So the current here, looking at this equation, 44 volts equals 44 ohms times I1. That means I1 is 1 amp. Woo, 1 amp. That's an easy number to write down. So I1 is 1 amp. Now, I went back, I guess I'm not showing all the details here. You can go back and back solve here, or you can start up here again, which I kind of like doing, or start here, and instead of using the 9 and the 1, you can use the 1 and the 5, or the 5 and the 1 here, flip those, multiply the equations. Especially if I have enough time. I like to solve the I1s and the I like to solve those independently, and then I can check and see. It's a way to double check my numbers. If I've made a mistake in I1, immediately back solving will give me a wrong number for I2. Okay, at some point it's nice to go back and check, and that's why if I have time, I do independent calculations of I1 and I2, and then check and see if everything matches up correctly. All right, so I did that and I got 1 amp, and then I3 was the combined of those. So hey, this isn't so bad. There's 1 amp going here. There's 1 amp going here. When the two individual 1 amps come together, they become 2 amps and go backwards through that battery. So that's it. So part A was asking to go in and solve for all the currents, and we got them. We got all the currents for that circuit. And yeah, this was on a midterm, and so I tried to provide some fairly straightforward numbers, so you weren't, so students wouldn't have to deal with crazy decimals. Anyway, then what the question asks about is go in and find out what are the voltage drops across all the resistors. Well, we can do that. So the voltage drops across each of the resistors then, let's see if we can match this up. First of all, I can take any individual resistor and I can take its resistance times the current. That's going to give me the voltage. That always works. If I can look down at individual devices in a circuit, I can always use for a resistor, I can use that formula. If it's capacitors, you can use the formula for capacitors, if that's the case. And so I've got 4 volts across resistor 1 and 8 volts across resistor 2 and 2 volts across resistor 3. And now I'm going to do another check here. What I'm going to do is go through and see how I've taken the circuit and I've drawn a little point at all the junctions between all the devices. So I've got a battery here, battery here, battery here. Notice you can move resistors and batteries back and forth, and capacitors as well, along any individual branch. If it's going to make the problem easier to solve, go ahead and do that, right? Go ahead and switch the batteries and the resistors to where you can kind of see the pattern in what's going on. So I got all the voltages. I want to go back and double check. So I decided, hey, this is an easy place to define as 0 volts. It's at the negative terminal of all the batteries, at least the way I've written it. So this voltage here, that's going to put me at +8. So that's what I wrote in. Now the writing here is a little small. You'll be able to see this when you look at the slides. But that I wrote as 0 volts, 0 volts, 0 volts. And then this battery was 8 volts. That's going to give me an 8 volt boost. And R1 is 4 ohms. And 4 ohms times 1 amp. So I'm looking at R1 times I1. That's going to give me a voltage drop of 4. So I'm going to go from 8 volts. If I continue and drop voltage through the resistor, it's going to drop me down to 4. So that's a 4 volt here. Now this branch also was 0 volts. And the battery here, that can put me at 12. Why is there not a 12 at that location? I don't know. Okay, there should be a 12 written right there. See that 12? There it is. So there's a 12 right there. And then I'm going to go through a resistor of 8 ohms. Now this also was 1 amp, so that's going to drop me by 8 volts. So the battery boosts me by 12, and the resistor drops me by 8, and I'm at 4, which is good because these two are essentially the same point. So let's see if that last one works. We're good. If I start here at 0, now I'm going opposite the current, but that's going to be okay. I go from 0 to the other side of the battery. It's going to take me from 0 volts to 2. So that's 2 volts. Now, I do have to pay attention now because the current's going the opposite direction. And that means that if the current's going this way, this side of the resistor, current's going this way, this side of the resistor is at the higher voltage. There's a voltage drop in the direction of the current for a resistor. For battery, it doesn't matter. The terminals on the battery, the positive is at the higher potential, the negative is at the lower potential. I don't have to know what direction the current's traveling. But for a resistor, I have to know what direction the current's going. Current is going to go through a resistor, and the voltage is going to drop. The voltage will be lower once the current has passed through the resistor than it was at the outset. So this resistor is 1 ohm, and that's 2 amps. 1 times 2 is 2. And that says that there's a voltage drop from here to here of 2. Well, that means if I go this direction, it's an increase. And I got 4 volts all the way through. So it matches up. Good news. Everything seems to have worked. Okay, that's good news, right? Okay, everything looks consistent. Problem 2. Problem 2 on this practice set of problems, it says in the circuit below, There's the switch. I found the switch. The switch is going to get closed, and when the switch closes, we're going to charge that capacitor, right? This is kind of a standard RC charging setup. And we're going to be charging the capacitor right here, this 20 microfarad capacitor. Now I got a resistor in here, and the resistor is at 575 ohms. So that's what we're looking at. Now the things it's asking us to do, find the time constant, and that's just R times C. I think we can do that. Draw plots of the current as a function of time. Draw a plot of the capacitor charge as a function of time. So you guys have been doing all your lab reports, and you're putting together all those graphs, and that's good, because you're practicing thinking about the graphs and making sure that the graphs make sense. So that prepares you for the midterms. So I hope you guys aren't saying, oh no, somebody else was doing the graphs for me. That's not a good thing to hear at this point. So definitely all that practice with graphs is going to come in handy here. So draw plots, find algebraic expressions to show the rate of energy dissipation. So an energy rate is a power. So that's what we're going to be after there. And then finally, an energy rate for the capacitor. So three things are happening here in terms of energy. So it's the problem on the right. I have a battery, and the battery is providing energy. So there's a power, there's a rate at which the energy is putting energy out in the circuit. So that's the power of the battery. Now the power of the resistor, trying to get the light just right in here, but I'm going to go back to a little less light. There we go. That'll work. So we have got a 10 volt battery. Again, we have the 575 ohm resistor, 20 microfarad capacitor. And what we're looking at in terms of power is the battery is providing energy at a certain rate. Now energy is conserved, so it's got to go somewhere. Where are the two places the energy could go? You go, well, it could go to the resistor, or the energy could go to the capacitor. Now if the energy goes to the resistor, what does the resistor do with the energy? And it takes electrical energy and converts it into thermal energy. It just heats up. Now, it's not likely we're going to get that energy back in the circuit. Once the resistor is heated up, that thermal energy tends to spread out through the environment, and it's not going to be recoverable. Capacitors, on the other hand, are going to store that energy. So what's going to happen is energy is coming out of the battery at a certain rate. Some of the energy goes to the resistor, some goes to the capacitor. Now this is a moving target. Things are changing when we charge up the capacitor. There's going to be a rate at which energy is going into the capacitor. There's going to be a rate of energy going into the resistor. As time changes, that's going to be changing. So let's get this from the start, I guess. Part A says, what's the time constant? Now remember, time constants are, I can graph those, because for the exponential drop-off, one time constant tells me when the current, in this case it's the current will have dropped to 37% of its original value. So if we're using the exponential approach to asymptote, which is what charge is doing on the capacitor, that function during one time constant will grow to 60, what did I say before, 37%? This one must be 63, right? I think those are the numbers. Let's see, on the way down, one time constant is 37, right? And then 14, and then 5. And then on the way up, one time constant takes us to 63, two time constants takes us to 86, three time constants takes us to 95, I think. And we talked about this in class too. exponentials are just everywhere. Exponentials are your friends. So you want to, spend, it's worth spending a little bit more time playing around with these exponential functions and getting to know how they behave. Because they're not going away. They're going to show up everywhere in whatever science or engineering field you end up in. Exponentials are great, so embrace them and get familiar with how they operate. So here are the two graphs, and you want the graphs large enough, let me say that, on these midterm problems, because you guys know by now I ask you to draw graphs. So I think we've drawn graphs, right? So make sure that you get them labeled. This is current in units of amps, and this peak value, this starting value is I naught. This is time, measured probably in seconds. Here is a nice representation of an exponential curve. This is showing one time constant. For the charge on the capacitor, we're charging the capacitor. That's the function. And so the Q naught is not the starting charge, but it's the asymptote. Q naught represents an asymptote value for an asymptotic value for charging the capacitor. And for this flipped over exponential, one time constant takes us up to 63%. Okay, so I got that labeled. I got oh no! Oh, I can't believe it. I labeled this as time? No, this is, it's Q of time. Never mind. I didn't quite, these units should be coulombs, right? Or nanocoulombs or something. This is Q as a function of time. This could be current as a function of time. Maybe this is the one I should change. I should say this is I as a function of time and then put amps somewhere else. Okay, sorry about that. I promise not to take off any points if you guys do the same thing in the midterm. So putting the values in that were given, we were able to determine V over R. The current's going to start off at 17.4 amps. So that's a pretty good current that we're starting. How did that happen? That's not right. Is that milliamps? V over R is no way going to give us 17 amps. Those have got to be milliamps. Check those numbers. Okay. Yeah, that's got to be something different, right? The Q naught value is going to be C times V. Boy, I hope this makes more sense. 10 times 20 microfarad. Yes, 200. All right. Microcoulombs. So I think we got the right units and I think we got the right numbers, but this has got to be milliamps, right? It's got to be milliamps. Okay. I'm going to lose a point or two there, but that's not a big deal. On part D, we're doing all the power calculations. So here we go. Power, remarkably enough, for any device can be solved by taking V times I. And you go, well, sure, for a resistor, V times I works fine, but what about a capacitor? Yes, it works for a capacitor. It works for a battery. Any device in my circuit, I can do V times I. Now, I got to make sure I get the right V and the right I. So what I've done here is I've said specifically to find the rate of energy being used in a resistor, I need the voltage across the resistor times the current going through the resistor. Now I chose, because of, how did I choose this? I chose to take the voltage in the resistor and write that as R times I. So I ended up with R times I squared. Now the I's are time dependent. So that's why I did that, yeah, because I didn't do the voltage graphs. I didn't write down the voltage formulas. V and I both are going to be time dependent. So I took the voltage and rewrote it in terms of current, and then current squared became I naught squared, e to the minus t over tau squared, and that's why there's a factor of 2 here. So this is the formula that I came up with. Now I took the R times I naught, and I took out the I naught and replaced it with V over R. So I wanted to get it back in terms of the original values that were given, and that's kind of standard practice on our exams. So I ended up with V squared over R, where V is the 10 volts of the battery, and R is 575 ohms. And then I got the exponential. Now, you could have left that as a square or bring the two inside. I'm okay either way. In some ways, it's nice to have the square outside to show that we picked up an exponential factor both from the voltage and from the current. Okay. And when we do comparisons, it may be nicer to have those two separate factors. I did the very same thing with the capacitor. I took the voltage across the capacitor, the current. Now, it's this problem. The current is the same, right? So since it's a single loop circuit, everybody's got the same current. The current in the battery matches the current in the resistor, matches the current in the capacitor. And yes, current flows through a capacitor because whatever goes in one side matches what comes out the other side, even though the charge never quite crosses through there, right? So anyway, I got current going through capacitor, current going through resistor, current going through battery. They all match. They're all given by that formula. And so I substituted one factor of that in. There's my I naught, and there is the time dependence on I naught. Now, the other factor that I needed here was voltage, but I didn't do the voltage, I did the charge instead. So I took the voltage and rewrote it as Q over C, and the Q has time dependence, and the Q time dependence is Q naught times the 1 minus e to the minus t over tau. All right, so that's what I did. And so I got one factor of time dependence from the Q, and I got one factor of time dependence from the current, and they're opposing each other. So whereas, let's see, this was the power formula for the resistor, and we said for the resistor the voltage is dropping off, the current is dropping off, I'm just going to get this exponential drop off. Initially the resistor has a lot of energy going into it, it's generating a lot of thermal energy, but as the current drops down, the resistor is generating less and less thermal energy. Eventually the current's going to stop, right? And then the power will go to zero at that point. Compare that with the capacitor. Now what's happening with the capacitor is as the charge builds up in the capacitor, that's this first factor. As the charge builds up, there is going to be a pretty fast rate of energy going into the capacitor. So initially, this factor right there, this effect with the charge, means that energy is coming into the capacitor pretty fast. The largest slope here is right initially. So it's coming into the capacitor really fast right to start with. Now, the second effect on the capacitor is that, again, the current's going to drop off, and that means that the slope on this is going to level off. And so what I've got is I've got a 1 minus e to the minus t over tau factor, and I've got an exponential factor. And what that leads us to is something where we rise at first, but then we drop off, and I'm not sure about that curve right there at the first. I'm thinking, why is that there? I'm thinking that it starts off with a slope because we're taking this and multiplying by this. That's what these two factors are telling us. So I'm thinking, first of all, we can erase that line. I'm thinking that it's going to start off with a pretty good slope and then reach some kind of a peak and then drop off again. Because again, we're taking this factor of increasing charge and multiplying it by the drop off in the current. Okay, so the power in the capacitor, that's the formula. I was able to get this in terms of V squared over R, which is good. So everything's got the same coefficients out front. We can do an easy comparison. V squared over R, V squared over R, and then we can look at these two factors here. Now, question then, it's not on here, it should be on here. What's the power of the battery doing? if we wanted to find out what's the rate of power coming out of the battery, well, the power coming out of the battery should be V times I for the battery. Now, for the battery, the voltage is fixed. When the battery is running its chemical reaction, all of the charges get the same amount of energy. So the voltage is fixed. That's not dropping off for the battery, but the current is. So for the battery, I just take a factor of V and multiply it by the current. I'm going to get V times I naught, which again is going to give me V squared over R. I'm going to get one factor of exponential drop-off for the battery. So that's what's going to happen. Okay. Interesting. How would we determine how much energy the battery provides while charging this capacitor? And to do that, you would integrate these functions from 0 to infinity. So, you know, by the time the capacitor is fully charged, we might as well just integrate out to infinity to include all that. The area under these curves will tell us how much energy has been thermalized in the resistor and how much energy is stored in the capacitor. Now, the capacitor energy is still available for the circuit. The thermal energy generated by the resistor probably has dissipated out, spread out through the environment. It's not going to be recoverable. Anyway, try this. We may have done it. I'm trying to remember if we did that example in lecture. It turns out, I believe, if you try this, you find out that anytime you're charging a capacitor, half the energy goes to the resistor, half the energy remains in the capacitor. So to get a capacitor stored with energy, you have to dissipate an equal amount of energy through the resistor. Check and see if that's the case. I believe it is. All right, let's look. It looks like we're through that. We're time to move on to problems 3 and 4. So we've looked at the circuit examples from chapters 25 and 26. Now we're ready to take a look at the magnetic field examples. So let's do those. With problem 3, it says that we have a wire with 8 amps going through it. And next to the wire is another set of wires. Now this is a square. How many loops are here? I always forget to read the number of loops. This time there's only one loop. I think I read it carefully and there was only one loop, right? You guys double check that. You guys see any numbers of loops on that? All right, here we go. So what's going on is some kind of a power supply is maintaining a steady current of 8 amps here. Another power supply is, there's wires coming in here. Wires are coming in, connecting, and they're maintaining a steady set of current going through this square. So these would, I believe, the way the problem is set up, they're not inducing currents. Okay, so that's the thing I want to be clear on here. What we've got going on here is not, we've got 2 separate sets of currents, and those currents will exert forces on each other. Those forces may be equal and opposite, or they might not be. Remember, magnetic forces don't have to be equal and opposite. So that's kind of an interesting feature of magnetic forces. So anyway, separate power supply driving this, separate power supply driving this. I got the dimensions, I know the currents. Let's go in, what are they saying? Okay, so they're not asking about forces on each segment. They're asking about the total force. But I think that means we got to go in and solve for the force on each segment, or at least look at the force on each segment. So it's specifically the force that the square experiences as a result of I1. They could have asked us to solve the other way, but they didn't, and I'm glad they didn't, because that turns out to be a much harder problem. So we've actually got current 1, that's a bunch of moving charges, charges in motion will generate electric and magnetic fields, and those electric and magnetic fields will exert forces on other moving charges, and those other moving charges are in this square. So I'm going to start by saying a constant current is going to generate a magnetic field. It's not going to be an electric force effect, because even though current is flowing in the wire, it's not generating an electric field. I still have the same amount of positive and negative charge. The wire is not becoming charged. So the electric field effects will tend to cancel out, and I'm going to be left with a magnetic field surrounding a long, did it say it was a long wire? Yes. Okay, a long straight wire means I can use my Ampere's law approximation. So I'm going to use my Ampere's law approximation formula right here. That's current 1. And let's see, what are the distances that we have to consider here? RA and RC, I labeled these. I called this branch A, this B, this C, this D, and the distance out to current A is 4 centimeters, and the distance out to C is 22 centimeters. Now, if I were solving for the force on those charges going vertically, I would have to do an integration, but they didn't ask for that. So I'm gonna do this instead. I'm gonna say, look, looking at the direction of the charge, that is going to be, I did draw the magnetic field. There we go. All the x's are showing the direction of the magnetic field in that region. So those x's are all going into the board. They're coming back out of the board up above, but here they're going into the board. And if I have a current going this direction through a magnetic field, let's see, it's positive. I'm treating current as a positive charge moving in that direction of the current. My right-hand rule is telling me that that's going to be a force upwards. And we've looked at those examples, right, where we have two currents parallel will attract each other, and anti-parallel will repel. So that looks like what we've done before. And then here, I'm going to get repulsion, because that's anti-parallel. But the repulsion effect will not be as large as the attraction, and that's because the distance is larger. So between this section A and section C, I have a net force upwards. Now, what's going to happen with B and D? As I step through section B, I'm going to have a force in this direction, using the right-hand rule, and D is going to have a force in exactly the opposite direction. But what I can do is, at each step along sections B and D, the forces will cancel out. They're going to start out being larger at the top, and then as we come down, they're going to get lower and lower, but they'll match on the two sides. So since the problem is only asking about a net force on the entire square, now I've asked it both ways before on midterms. So I've done similar problems where I've asked for the force on each segment, and that would mean integrating these two. But if you did that and carried them out, we're guaranteed those two effects would cancel. They would be equal magnitude, opposite direction. All right, so I can ignore those two sides. I just need to find out what force A is. It's going to be in that direction. Find out how much force I have along section C. It's going to be in this direction. So I did that by using I times L times B. Now the B is B1. It's the magnetic field due to current 1. So you could think of this as putting a 1 right there and 1 right here and here, and say, okay, current 1 is generating a magnetic field. Current 2 passing through that magnetic field will experience a force. So these have canceled out, and putting numbers into each of these and getting everything in there correctly, little k is still 8.99 10 to the 9th, or round off to 9 times 10 to the 9th, works well. L was 0.18 meters. C is our space-time conversion factor. It's the speed of light. This is 3 times 10 to the 8th. And I ended up with 10.8 newtons, micronewtons. Don't get carried away with this. So it's a tiny effect. And the currents that we have are, how big were the currents? Ooh, 8 amps, that's not tiny. 1.5 amps, that's pretty good. Pretty good sized currents, and they're only 4 centimeters apart. But the force that I'm getting, the magnetic force, is only turning out to be, 11 micronewtons minus a couple micronewtons in the other direction. I'm ending up with 8.84 micronewtons. The net effect is upwards. All right, questions on any part of that? So you can see how you have to step through. What would happen if they ask it in the opposite direction? If they said, what force is current 1 experiencing as a result of this square of current? That's hard. I would have to find out what is the magnetic field due to this square loop. And I would have to do section by section and then piece all those 4 magnetic fields together. That sounds like a lot. And then, once we get that, we would have to find out what the value of the magnetic field is right along the path of current 1. And once we get that, then we just use the ILB. But that's a much more complicated problem. Okay, so it's a good thing they ask it. I would never ask it the other way. So don't panic. I'm not hinting around that you should be able to do the other approach. That's not true. So practice this way, and maybe practice doing it in 4 separate segments. Go ahead and solve. Practice solving what that value would be. But I think you're going to be fine with that approach. All right, we are ready to move on to our last example here, problem 4. We got an electron. It's got a kinetic energy of 700 eV. Now, when we generate beams of electrons or protons or whatever, it's very handy to put their kinetic energies in terms of eV. And that's because, what's the charge on an electron? Well, the charge on the electron is E, and the charge on a proton is E. And that means that I can quickly say, to get the electron moving with this much kinetic energy, I need 700 volts. Okay, I didn't need a calculator for that. I just factored out the E. So the voltage I would need to get an electron up to that speed is 700 volts. And that's why we use it. Now, to carry through this problem, I'm probably not going to be able to keep this in EV. I'm going to have to switch units. I'm going to have to switch units over into joules. I got to go into standard units because, let's see, what other units are we going to have here? We've got Tesla already. Tesla's a big, complicated combination of standard units. I got to have joules so that things are canceling out behind the scenes. EV is not going to cancel out automatically. So my guess is the first thing we got to do is get the energy, the kinetic energy in joules, get that converted correct. So it's a check to see if you guys know how to do the conversion. And then I've got a magnetic field, 400 microtesla, and the magnetic field direction is given here. It's uniform, and it's directly into the board. So that's a good thing. The magnetic field is the same at every location. Now, the electron is going to come in here, and we know from looking at magnetic fields, the electron is going to experience a force sideways, right? Magnetic forces are so interesting and can be kind of confusing because of this sideways effect. We're used to thinking, at least I was used to thinking before I was introduced to magnetic forces when I was a freshman in college, gravity, electric forces, everything is either attractive or repulsive. And magnetic forces are different. They're sideways, right? Anyway, so here's the direction of the field. And the velocity of the electron is going to come in this direction. Now, I guess the first thing we have to do is it says draw a trajectory that you might expect. I haven't got on to this yet. I just want to talk about the setup a bit. The electron is either going to experience a force to the left or a force to the right. Those are the only possibilities. If it's positive, it's going to be one way. If it's negative, it's going to be the other. The electrons are negative. Which is it? Now, since it's an electron, it's negatively charged. I'm going to use the left-hand rule. I'm always looking for opportunities to do that. And so my thumb, I'm going to say that's the direction the electron is coming in. The magnetic field is into the board, and my palm will be facing in the direction of force acting on a negative charge, and it's going to be perpendicular to velocity. Now, as the velocity shifts, it's going to remain perpendicular. So it's going to go into a circular path. Now, I know that I can calculate the radius of that path. So that's the first thing we want to do is get a radius. Here's the mass of the electron, and we know the charge. There's a couple possibilities here. If r is really, really small, it could be the electron comes in and does half a circle and stops over here somewhere. It could end up striking one of these locations. If the r is a little bigger, then the electron could end up over here somewhere, right? So there's going to be some values of r which will have it hit here. Some values of r will have it hitting this side. The largest values of r will have it hitting the side opposite that region that we've defined. So let's take a look and see what we've done here. Okay, so I talked a little bit about how are we going to get the electron speeded up. We're going to generate a 700 volt region and multiplying that by the charge of the electron. It's going to give me a kinetic energy of 700 eV. And you know, I didn't put the minus sign in. In effect, the minus sign is being taken care of with the direction of the negative and the positive plates that we've defined. All right. Now, that I switched over and did this instead. So it's Q times V. So instead of doing 1E, I changed that to 1.60, 10 to the minus 19 coulombs. Now a coulomb times a volt, and E times a volt is EV. But a coulomb times a volt is a joule. And the kinetic energy worked out to be 1.12, 10 to the minus 16 joules. So that's the number that we have ended up with for the kinetic energy. Now, we can take that kinetic energy, 2 times the kinetic energy, divide by the mass. This is the old kinetic energy 1/2 mv squared. It looks a little different because we're solving for V, but that's the formula here. It says that the speed of the electrons coming in is 1.57 10 to the 7 meters per second. Now, passing through a uniform magnetic field will not affect the speed of the electron. It will only redirect it. So the speed of the electron is going to be essentially constant traveling through that region. So now the formula that we've derived, and I should have gone back and re-derived it, but I didn't. I just wrote down mv over qb. I guess you guys maybe can get away with that unless the problem specifically says derive the formula. So this came from looking at circular motion and the magnetic force equations. In any case, I ended up with a radius of 22.3 centimeters. So that's what I have right there. And looking at my diagram, now the point it's coming in at is at the midway point. At least that's, I don't know that it said that. I think that's just assumed. So that distance right there would be 12.5. Now, 22 centimeters sounds like that's a big enough radius of curvature that's going to hit the other side. I'm not sure, but that feels like that's what's going to be happening. I can double check that. What I can do is I can start right where the electron comes in and travel over 22.32 centimeters and draw a point there, and then I can get my ruler out and see where 22.3 takes me. If 22.3 takes me to here, then that's the wall I'm going to hit. If 22.3 takes me to here, that's the wall I'm going to hit. So I can get that ruler out and see, and when I tried this, it turns out that, yeah, it's going to hit the opposite side. So that's the side that we're going to end up at. And, oh, there's my, my vector diagram saying that the force on a negative charge would be in this direction. And so what happens is, as we curve, the force, the velocity keeps changing, and the magnetic field direction also. So I did some trig or geometry, something here. What I did was I drew in the radius up to here, and I drew in the radius here. It's circular, so there's going to be a center to that circular motion. There's nothing located at the center, but it is going to still be circular motion. And so now I have a curve. That's going to be a right angle here. This is going to be a right angle here. I can come across to where this point's located and drop a perpendicular to this other line. And now what I've got is I've got a right triangle. I know the distance to this side, that is 12.5. And I wrote down Pythagorean's theorem for that right triangle. And what it looks like is I solved for x. So I said x squared plus 15. Yeah, so this side is 15. I was looking for the 15. It's over here. So 15 is right here. That's 15 squared. X squared plus 15 squared will be r squared. Plugging in those numbers, I ended up with an x value of 16.5. So, and then a, r minus x is 5.79. So I just need enough information. It said this. It says, where will it hit? So I need to be able to identify the particular location. So if I take a path straight through here to the other side, that seems obvious enough. If I now move 5.79 centimeters off in this direction, that's where it hits. The total distance, oh, I don't think I scaled this very well, because the total distance is like 12.5, right? It's actually more like this. I don't think I got everything quite drawn right. I don't think I checked, maybe these distances. Something's not quite right with my diagram. If you did this well on the exam, you would get full credit. There's enough stuff going on here. Everything is labeled well. It's not quite drawn to scale, but it looks pretty good. So this looks pretty thorough to me. Anyway, that's it. Once I've identified these distances, I've identified unambiguously, where is this thing going to hit. Okay, so those last couple problems, we're looking at magnetic forces and magnetic fields. Those are chapters 27 and 28. And so those two chapters, along with the earlier chapters. So we've got, we didn't get a problem on chapter 25, I guess. I apologize for that. Go back through, look at some of the homeworks on 25, look at some of the lecture examples. Those will be good. If you're looking at this early, and a lot of students have told me that they have looked at this early, so they got an early start on these. That's good. So these are definitely, in addition to the lecture examples and the homework examples, these are good examples to work from. We've hit a lot of the really kind of key items going on in these 4 chapters. So let me know, whatever questions you guys have, stop by, we'll get those looked at.